The high ionization energy will always occur after an atom loses its last valence electron. So for the first group, it wanted to lose 1. It does not want to lose the second, so that'll be a high second. Group 2 wanted to lose 2, it does not want to lose 3, so that'll be a high third. And we really can just continue then all the way across the row. High second, high third, high fourth, high fifth, high sixth, high seventh, high eighth, and then finally in group 18, where they had 8 valence electrons, they really didn't want to lose their first valence electron. So both these places where we have first written, that would really be just the initial ionization energy that we talked about in the last section. So now what this is going to allow us to do is really compare elements within the same period on the periodic table. So let's say that we want to look just at these elements in period 2. A quiz or a test question might ask you which of the elements in period 2 has the low second ionization energy. You're going to have to remember low means that it's easy. Low second means that it wants to remove the second. That's why it's so easy to take it away, which means it's going to have 2 valence electrons. So if we think about the valence electrons that each group has, the low occurs when the number from the question matches the valence electrons. Beryllium would have a low second. I could also ask you for a high ionization energy, so maybe a high third ionization energy. Remember, high means it's hard. It means it's harder because it already is stable, which really means if I'm asking you for the high third, you just have to drop back down a number, and that will match the valence electrons. High third means it wanted to lose 2 and only 2, which means it has 2 valence electrons. So again, that answer would also be beryllium. If we're looking for the lows, you just number your valence electrons. If you're looking for the highs, just start with a 2 instead and move the 1 to the end. So high fourth would occur in group 13. Low fifth would occur in group 15. And that's really all there is to the successive ionization energy, which is almost the very end of our periodic table discussion. Because the last trend that we're going to be looking at for today, and really the last trend that we're going to be looking at for the entire unit, is the electron affinity. And the electron affinity describes the amount of energy that is required to actually add an electron to an atom. Okay, so electron affinities can actually be positive numbers or negative numbers. And all that means is that sometimes when we look at adding an electron in, we actually remove energy. That's a negative number, it's going away. And sometimes when we add an electron in, it will be a positive number, which means that the energy is being added. Now the reason that we're making such a big deal about this and the reason that it gets to be its very own trend is because that numbering convention can be a little bit confusing. Either way, we're referring to adding electrons in, but some atoms actually want that. They want to become negative ions, in which case they actually wind up with a negative number. High electron affinity means they have a big affection for electrons. They love electrons a lot. High electron affinity will actually be expressed as big negative numbers. And that just means that the atom is willing to pay to get the extra electron. It's willing to actually get rid of energy in order to be able to take that electron in. Low electron affinity just means that the atom does not want any extra electrons. It doesn't want to become a negative ion. Positive numbers are actually the lowest of the electron affinities. They really, really, really do not want the extra electrons at all. And positive numbers are actually pretty rare. Most atoms lose energy when they gain an electron, but some actually need to be paid to take those electrons in, and that's where you wind up with low electron affinities. So overall, as you go across, if you think about how badly these atoms want extra electrons, you can probably think of the trend. We know that fluorine really, 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 really wants an extra electron to become stable. We know that fluorine has the highest electron negativity. We know fluorine really, really, really wants that extra electron a lot, which means fluorine is the biggest negative number. And really, everything in group 17 have incredibly high electron affinities. And I'm just going to write down here that that means big negative number. They're losing a lot of energy, they're becoming a lot more stable. And overall, as you go across the periodic table, electron affinity does increase. Their affection for electrons gets bigger and bigger, which really just means they become bigger and bigger negative numbers across. So for the most part, we could just fill this in. And we're really only going to worry about the main group. We're not going to worry about the center here. By just going 17, 16, 15, 14, 13. All of these are moving towards becoming more stable. I'm guessing you probably were able to guess the group that really, really, really does not want an extra electron. They're going to have an incredibly low electron affinity. They're actually going to wind up with a positive number because they really don't want another electron added. The somewhat surprising part, and the thing that you're going to have to remember, is that group 2 is actually the other group that winds up with a positive electron affinity for most of its members. And then group 1 is in the middle. So if we look at this and we try to figure out what is it about group 18 and group 2 that means they really don't want another electron, whereas all of the other groups, they're all right with it, and it gets bigger and bigger, or more and more affinitive, more and more negative numbers as we go across. And in order to easily figure this out, we really just need to think about our orbital notations. Let's look at sodium. Sodium's orbital notation looked like this, the shorthand version. We could potentially add a second electron in right here. There was already space. That's why sodium winds up being a negative number, because there's a spot for it. But if we look at magnesium, which is what this is now starting as, magnesium, you might notice that in order to add another electron in, we actually have to create another room. That would be magnesium with a -1 charge. If you have an empty spot available in an orbital notation, if there was an empty bed that an electron could get filled into, then it's going to be a negative number, which means, as we move across here, higher and higher electron affinities. But if every bed that's in the room is already filled, like magnesium was, or like argon is, if all the beds are already filled up, if there's no place in an open room for the electron to go, then you're going to have to add energy in to basically create that subshell. So if we think about the general trend for electron affinity, it does increase as you go across. We know fluorine really wants the extra electrons, but you do have to remember to take out group 2 and group 18, because that's two places where we already had full subshells. And if you already have full subshells, they really don't want another electron because there's just no room within their orbitals. And that's really all there is to electron affinity. You just remember that it increases as you go across. Fluorine has a very high electron affinity, which means a big negative number. But after you think in terms of increasing going across, you just pull out the two groups that are kind of exceptions. Group 18 is an exception because even though it's the whole way across, it really doesn't want the extra electron. And magnesium is also an exception just because it already had a full subshell. And that is really all there is to the periodic table unit. Of course, you can email me if you have any questions. Otherwise, good luck on your test.